Hey guys, welcome back to WD Explains. I'm Wilson, and today we're going to be looking at what happens when we try to find the pH of a dilute acid and how we solve the problem. So first, we're just going to solve this question. We're going to find the pH of a solution with a hydrogen concentration of 0.25 molar. So we just use our simple pH equation. So pH equals negative log 0.25 because that's our given hydrogen concentration. And if you calculate this, I encourage you to, it's going to be 0.602 roughly. So we know that acids are supposed to be between 0 and 6.99, and we know that this is an acidic solution, so this answer checks out, super acidic. So let's see what happens when we try to find the pH of a solution with a hydrogen concentration of 1 times 10 to the negative 8 molar. So very, very, very small. So here our pH is going to be equal to negative log 1 times 10 to the negative 8. I'll let you guys calculate that for a second. Okay, so if you put that into your calculator, I'll give you a couple more seconds. Just pause it. So the answer we get here is actually 8. So if you guys don't believe me, calculate it yourself. So we're actually seeing that this super low concentration acid is giving a basic pH, because we know that acids are from 0 to 6.99 and bases are from 7.01 to 14. So what is going on? Why is this acid giving us a basic pH? So is this dilute acid acting as a base? So no, but why? Why no? So what is happening? So you guys probably know we have a constant called Kw, which is the ion product constant for water, and it always equals 1 times 10 to the negative 14. And here's the equation. So when you have any sample of water, no matter how acidic or basic, no matter what, when you multiply the hydrogen concentration by the hydroxide concentration, it will always give you 1 times 10 to the negative 14, no matter what. So that's a very key assumption, very key thing we need to know here. So when we have a regular neutral sample of water with nothing added, the concentrations of hydrogen and hydroxide come out to 1 times 10 to the negative 7. And then they're multiplied by each other. And then we know our exponent rule. When you multiply bases, you add the exponents, and negative 7 minus 7 is negative 14. So 1 times 10 to the negative 14. But if you guys notice, maybe you don't, maybe you do, 1 times 10 to the negative 7 is actually bigger than 1 times 10 to the negative 8. So what does that mean? So, if you guys didn't guess already, the hydrogen concentration in the water is actually higher than the concentration of the hydrogens coming from the acid. So yeah, 1 times 10 to the negative 7, let's say this is H2O hydrogen, is higher than the acid hydrogen, which is 1 times 10 to the negative 8. So what does this mean for us? So this means that when we try to use the acid's hydrogen concentration to find the pH, it's almost as if we're taking the pH of a basic solution because it's so low, even though it's still an acid. So what can we do? Do we just add the concentrations? So do we do 1 times 10 to the negative 7 plus 1 times 10 to the negative 8? No, we can't. It doesn't work that way. It's never that easy in chemistry. So what we actually have to do here is make a quadratic formula to solve for hydrogen. And that's just the way we have to do it. That's how it's been figured out. So how do we do this? Well, first we got to write down what we know. So we know that we have our, we'll say it's hydrochloric acid at 1 times 10 to the negative 8 molar. And we know this is going to dissociate into hydrogen ions and chloride ions. We also know that we have H2O here, and it's going to dissociate partly into hydrogen ions as well, and hydroxide ions. So another key assumption we have here is we have to do something called a mass balance. Now mass balance is just stating that the ions that are coming off of both of these solutions. So we have hydrogen coming from 2 as our cations, are positive ions. And then we have chloride and hydroxide coming over off of the others as our anions, or negative ions. So the total amount of positive ions has to equal the sum, or this could be the other way around too if it was something different. But the total mass or concentration of the hydrogen ions, the positive ions, has to equal the sum of all the concentrations of the negative ions. This is something we have to know. And then we also have to use our formula. Kw equals hydrogen times hydroxide. Okay, so we've got all this laid out. Now what? Okay, so what concentrations do we know? We know that our chloride is 1 times 10 to the negative 8. All right, that's one thing. We know Kw is always 1 times 10 to the negative 14. Okay, so we don't know our hydrogen. We don't know our hydroxide. So you may think we're kind of stuck here. But what we can do here is we can actually create a variable. So if we look closer at this equation, we can substitute in our number. So we have hydrogen equals 1 times 10 to the negative 8 plus, and here's where we're going to create our variable. We're actually going to turn hydroxide into X. So now we have hydrogen equals 1 times 10 to the negative 8 plus X. And so we're not just going to turn hydroxide into X in this equation. We're also going to turn it into X in the Kw equation. So now we have Kw equals hydrogen times X. Now, we've also just created this stand-in for hydrogen. So we're going to substitute everything in, and we're going to end up with, over here, Kw equals 1 times 10 to the negative 8 plus X times X. And this is our equation that we can use to solve. So how does this work? So let's just quickly review it in case you're confused. We used our mass balance equation to set hydroxide as X, and we used our known concentration of chloride from our acid to set hydrogen as the concentration of chloride plus X. We use this equation that we just set right here to solve Kw, because we switched the hydroxide in Kw to X, and then we can switch this in so that we only have one variable to solve for instead of two here. Now we just have X. We've operationalized things so that we have just X's in the equation and everything else is a constant, so we can solve. So how do we do that? We have Kw equals, we'll just distribute this. So Kw equals X squared plus 1 times 10 to the negative 8 X. We'll do the final step. We'll make this a quadratic by making it equal 0. We'll not make it a quadratic, but make it solvable. So we have 0 equals X squared plus 1 times 10 to the negative 8 X minus 1 times 10 to the negative 14. If you guys remember, that's our ion product constant of water. Or just our Kw, as I usually refer to it as. So we're going to have to use our formula. All right, so we'll take our equation. We'll put it into our quadratic equation, which, if you forget, is X equals negative B plus or minus the root of squared minus 4AC over 2A. So we have X equals negative 1 times 10 to the negative 8 plus or minus the square root of 1 times 10 to the negative 8 squared minus 4 times 1 times negative 1 times 10 to the negative 14. Now I'm going to kind of rush through this. This is pre-calculated for me, but if you guys want to calculate it on your own, you guys can pause the video here. Excuse me. This is all divided by 2. Next row, we have negative 1 times 10 to the negative 8 plus or minus square root 1 times 10 to the negative 16 plus 4 times 10 to the negative 14 all over 2 still. This equals negative 1 times 10 to the negative 8. So square root of 0.01 times 10 to the negative 14 over 2. Step this up here. So we have negative 1 times 10 to the negative 8 plus or minus 0.000002 divided by 2. Now we're going to add here. We're not going to bother with subtracting, because if we subtract, we're going to end up with a negative number. And remember, the x that we're solving here is hydroxide. So if we have a negative number, it's not going to make sense to have a negative concentration. So we have negative 1 times 10 to the negative 8 plus 0.000002, which is going to give us 0.000019 divided by 2. This is still solving for x, remember. X equals 0.000095, or 9.5 times 10 to the 3, 6, 7, 8 times 10 to the negative 8. This is our hydroxide. So our hydroxide concentration equals 9.5 times 10 to the negative 8. So the easiest way to go from here is to calculate the pOH. So pOH is just like pH's evil twin. We have negative log OH instead, and it gives you the same. It gives you the pOH, and I'll tell you what to do with that in a second. So we'll do pOH equals negative log negative 9.5, or just 9.5 times 10 to the negative 8. So you guys calculate this out, it's going to be 7.02. Okay, great. So is 7.02 our final answer? No. Because remember, we're trying to find the pH. Everybody uses pH. pOH is just kind of something you use when you need to find pH, but you can't immediately. So 14 is always equal to pH plus pOH. So conversely, pH equals 14 minus pOH. So here our pOH is 7.02. So 14 minus 7.02 equals 6.98. And that is our pH. So if you guys think about it, we have this super low concentration acid. So 1 times 10 to the negative 8 HCl in water. So we have a super weak acid, so we would expect it to have an almost neutral pH, and that fits exactly what we found. So our pH is 6.98. So that's the end of this video. I hope you guys learned something. I hope you guys found this somewhat interesting, this pH paradox, and I hope you guys can use this at some point to solve a question. Thanks.